All right, in this video we're going to be looking at this average atomic mass worksheet. First part of this worksheet asks us to look at two different atoms and determine if they are isotopes. So for the first one here, I can tell already we have two different atoms. We have carbon and nitrogen. So because they're completely different elements, these are not isotopes of each other. Okay. For the second one, they are the same elements, both of calcium, but they have different mass numbers. Remember, this -40 and the -46 are the mass numbers. So both of these atoms have the same number of protons, but have a different number of neutrons because the mass numbers are different. Remember, our mass number is the number of protons plus the number of neutrons. So right here, like I said, because the number of protons are the same, the number of neutrons are different, this is an isotope. All right. This third one here, we have the same number of protons. So both of these have 12 protons, so we're dealing with the same element. But here we have 12 neutrons, and here we have 13 neutrons. So in this case, these are isotopes. Okay, this fourth one, we are dealing with boron for both of these. And if you look, the mass number is different. So again, the mass number tells us the number of protons and the number of neutrons. In this case, this is an isotope. And finally, this one has a different number of protons. So because the protons are different, we're dealing with a different element. So these cannot be isotopes of one another. All right. Number two, we're looking at the average atomic mass of hydrogen. So it tells us that our average atomic mass is 1.01 AMU. And then we're looking at two isotopes. We have hydrogen 1 and hydrogen 2. Remember, this 1 and the 2 are the mass numbers of each. So because our average atomic mass is 1.01, it is very, very, very close to the mass number of 1. So looking at the four choices here, I would say that D is the best choice because our hydrogen 1 has to be the dominant quantity for it to be that close to 0.001. So it makes sense that there would be the largest percent abundance of that isotope. Okay, for number 3, we're going to do the same thing. Our average atomic mass is 39.10. All right, and looking at the choices, we have masses of 39, 40, and 41. So 39.1, if we were to round it, is closest to 39. So I would say, and the question actually asks us to predict the abundance of 39. So because it's so close to that number, again, I'm going to pick the one that's largest. Okay, for number 4, we did this one in class, but I'm going to go ahead and do it again right now. So our average atomic mass, we find that by taking each mass, and we're going to multiply that by the relative abundance. Okay, and then we're going to add that to the other ones for all the different isotopes. So for this one, the first one, we have rubidium 85, and the percent abundance is 72.2. And for the second one, it's 87 and 27.8. And as I said in class, we can't work with percents. We need to convert this to a decimal. So you can do this a couple different ways. You can move the decimal to the left 2 places. So 72.2, I can move the decimal to the left 2 places. Or I can take that percentage and divide it by 100, which will give me the same thing, 0.722. All right, so I'm going to take each mass. So the first one is 85, and the percent abundance is 0.722. And I'm going to do the same thing with 87, 0.278. And when I multiply that out on my calculator, I get 85 35.56 AMU. And that is my answer right there. I don't need to divide by 2 or anything weird like we would with a normal average. We just simply multiply each mass by the relative abundance, and we add all of those up. All right, number 5 is pretty much the same thing, but instead of having just 2 isotopes, we have 3. So we have uranium-234 at 0.01, we've got 235 at 0.71, and then we have 238 at 99.28. So our first step is going to be, again, to take each percent and convert it to a decimal. So so not 0.01. This is going to be 0.01% is 0.0001. We have 0.71% and converted to a decimal, that is 0.0071. And then 99.28% is 0.9928. Again, move the decimal to the left 2 places or divide each percent by 100. And then our average atomic mass, same method. I'm going to take my first one, so 234. That's the mass. Multiply it by the relative abundance. I'm going to add that to the next one, 235. Multiply that by 0.0071. And then I'm going to add that to the third one, 238, 0.9928. And then when I multiply that out in my calculator, just be careful with parentheses, I end up with 237.98 AMU. Okay, looking at number 6 now. Number 6 is kind of tricky, I think. Nope, this isn't the tricky one I was thinking of. Still pretty straightforward here. So we've got 46 and 8%. We have 47 and 7.8, 48 and 73.4, 49 and 5.5, and then 50 and 5.3. So we've got 5 different isotopes this time. So this one's going to just be a lot of numbers. So again, our first step is to convert each percent to a decimal. I'm going to skip doing the conversions. I'm just going to go ahead and write them out as decimals. So our average atomic mass, we're going to take each mass. So again, I'm looking at the mass number, and I'm going to multiply it by the percent, but I'm going to convert this as a decimal, CIMAL. Not an English teacher. All right, so 0.08 multiplied by 46. I'm going to add that to 0.078, which is the second percentage as a decimal. Multiply that by 47. And then the third one is 0.734. And 48 is the mass number. And then 0.055 multiplied by 49. And then I have one more to squeeze in here, 0.053 multiplied by the mass number of 50. And when I carefully enter that into my calculator and crank out the numbers, I get 47.92 AMU. All right. Next, we are doing the same thing. But this one, they were kind, and they only gave us 2 numbers. So we have our percentage and our mass, and our percentage and our mass. So our average atomic mass, same method. I'm going to take each relative abundance, and I'm going to multiply that by the mass number. So the first one, 75.53, can be written as 0.7553 multiplied by 35, which is our mass here. And then I'm going to add that to 0.2447. I'm going to multiply that by the 37, which is that other mass. And this gives me a average atomic mass of 35.49 AMU. All right. Number 8 is the one I was thinking of earlier. Number 8's a little tricky. So number 8, we have our mass of 63, and that's the percent abundance right here. But the other isotope, it only gives us the mass, it doesn't give us the percent. So remember, our relative abundance is based off of all of the different isotopes that are there. So when we talk about our percentages here, they need to combine up to 100% because 100% is representative of all of the different isotopes that are out there. So to find the percent of the other isotope, the 65 here, we are going to take 100%, so the total number of all, or the total percentage of all the different isotopes of copper, and I'm going to subtract out the 69.09% of the copper 63, and that will give us 30.91%, and this is going to be for copper 65. Okay. At this point, once we've figured out the missing percentage, it's just a matter of doing the same steps as before. So our average atomic mass can be found by taking each percent as a decimal. So my 69.09 can be written as 0.6909, and the mass of copper 63, and then I'm going to add that to my other percent that I found, the 0.3091 multiplied by 65. And when I carefully punch that into my calculator, I get 63.62 AMU. All right. Number 9, kind of the same thing. We need to find a missing percentage. So we have our mass of 20 at 90.51. We have 21 at 0.27%, and then we need to find the missing percentage for neon 22. So same method as before. Remember, 100% represents all of the different isotopes. So I'm going to subtract out the 90.51% for neon 20, and I'm also going to subtract out the 0.27% of neon 21. This will give me a remainder of 9.22%, and this is going to be for neon 22. Same method as before when we set up our average atomic mass. I'm going to take each percent as a decimal multiplied by the mass. So the first one is 20, and that's right here. I'm going to add that to the next one, which is 0.0027. And this is for the mass of 21, and then 0.0922, which is for neon 22. And when I carefully put it into my calculator, I get 20.19 AMU. All right, finally, last one. Not sure why we have a box here. Okay, so for the last one, it's pretty straightforward. It's the same exact method that we've been using. This one, no tricks or anything. It gives us everything we need. So we have our average mass and our percentage. We have our mass and our percentage. And then we have our mass and our percentage. So we're going to set this up. No extra work that we have to do right off the bat, and except for converting everything to decimal form. So our first one had 78.7, which is 0.787, and then our mass was 23.985 AMU. Okay, and then our next one was 0.1013, and our mass was 24.985. And then 0.117, and our mass was 25.982. This gives us an average atomic mass of 24.4 AMU. All right, now the second part tells us that we need to use the periodic table to identify this element. So if we pull out our periodic table and take a look at it, we're looking for the element that has a mass, an atomic mass, that is closest to 24.4. So if you follow the periodic table and look at the number at the bottom, the average atomic mass that ends up being closest is magnesium. And that was the last problem on our sheet. If you have questions, shoot me an email or come in for extra help in the morning.